Welcome to this afternoon session for the CMAS 19th conference, and we'll get started in a few seconds. Okay, we'll go and get started. Good afternoon, and welcome to the fourth plenary of this year's CMAS conference. My name is Sarav Arunachalam with the UNC's Institute for the Environment, and I'll be the moderator for this session. In this panel, I have the pleasure of having three extraordinary scientists that we're lucky to have with us today, and I'll introduce them all to you shortly. The motivation for this session came from, of course, the pandemic that we are all in the middle of. A few scientists were making the case for the SARS-CoV-2 to being airborne, and how we need to pay attention that this mode of transmission for developing mitigation options. Lydia Moraska published this several months ago, where she made the case of the airborne transmission for SARS-CoV-2. And more recently, 200 plus scientists wrote a letter to the World Health Organization asking that we address the airborne transmission of the coronavirus. So with that, while this was being debated and discussed in the literature, a bunch of us started talking offline, and specifically Dr. Steve Hanna, who's on the panel. He reached out to a few of us, Dr. Venkatram, Dr. Weil, Jeff Weil, and myself, and said that the dispersion modeling community specifically should be involved, but they have not said much to this conversation based upon classic dispersion theory. So we had some email exchanges for the past few weeks and started to read all the papers that are coming out almost every day, and the news articles about the aerosolized nature of the virus. And then we decided that maybe we should have a panel discussion at this conference, given that this conference is about air pollution, air quality modeling. And at that point, I reached out to the experts, and I was very happy to have three different leading scientists in this community who could contribute to this discussion. So with that, I have three extraordinary scientists with us, starting with Professor Venkatram from UC Riverside. He will talk about the looking into a room to examine dispersion of airborne material, followed by Dr. Steve Hanna, whose topic is near field modeling for indoor and outdoor modeling of COVID-19 transport and dispersion. Either is it multibox, CFD, Gaussian, plume or puff, or K-theory. And then finally, we have Professor Glenn Morrison from the Department of Environmental Science and Engineering at UNC, who will talk about the not so surprising accuracy of indoor aerosol models in predicting COVID-19 outbreaks. So the way we've structured this panel is I laid out a few questions, charged questions to all the panelists. First, what do we know about the fate and transmission of SARS-CoV-2 in the air? How does this change in different microenvironments, specifically a room, such as home, school, office, etc., in a bus or an airplane cabin? What are mitigation options that one should consider to reduce infection? And finally, what are the research needs from a modeling perspective to better understand transmission of virus like SARS-CoV-2? So those are the questions. And the format is each presentation will be followed by time for the audience questions. We will end with an open forum discussion for all panelists. And I encourage the audience to please submit your questions via the Q&A widget. With that, we'll start off with the first speaker for this afternoon, Professor Venkatram. So Professor Venkatram is a professor of mechanical engineering at the University of California, Riverside, California. And his research is focused on the development and the application of models for the transport and dispersion of air pollutants over urban and regional scales. Dr. Venkatram co-edited and contributed to the lectures on air pollution modeling published by the American Meteorological Society. He was a member of the team that developed AirMod and was a principal contributor to R-Line, the US EPA model for R-Line sources. He's the recipient of the inaugural award from the AMS Committee on Meteorological Aspects of Air Pollution for contributions to the field of air pollution meteorology through the development of simple models in acid deposition, ozone photochemistry, and urban dispersion. His research on modeling the air quality impact of transport-related emissions was recognized in 2010 by the US EPA through a Scientific and Technological Achievement Award for improving the scientific regulatory community's ability to assess the impacts of mobile source emissions. His research on this topic is summarized in the monograph, Urban Transportation and Air Pollution. Dr. Venkatram.
Thank you very much, Sarav, for that nice introduction. So what I'm going to do is try to struggle to share my screen right now. And I'm going to share it. And then I'm going to go and hope everything works here. And you're going to see my screen. So hopefully you can see my screen, correct?
Yes, go ahead, Vinky.
Okay. As the title of my talk indicates, I'm essentially a person who does a modeling of dispersion in the outdoor environment. So as Sarav pointed out, a few of us got together and said, okay, let's look into a room to examine dispersion of airborne material. And it was motivated, this entire talk was motivated by statements, or at least statements by indoor modelers that appear to be inconsistent with what our understanding of dispersion is outside the room. So, so what I'm going to do is actually focus my talk on airborne emissions, airborne in the sense that these things act like tracers rather than as droplets that fall to the ground. So the reason I put up this is, you got a whole bunch of stuff coming out of a person's mouth when they cough or sneeze. What I'm going to do is just focus on material that remains in the air and acts like a tracer. So these are very small particles that act as tracers. I'm not going to say anything about droplets or what happens to them. I'll allow other people to talk about it. And first thing I'm going to do is I'm going to talk about what we understand about short-range dispersion outdoors. Then I'm going to talk about observations and models in the indoor environment. And what I'm going to do is try to talk about these models in the indoor environment through the lens of an outdoors person. So it's a slightly different view. And then, of course, I'm going to try to respond to what's Sarav's questions about those 4 questions he had. Sarav, if I don't respond to one of them, please forgive me. You can remind me later on to address them. Then I'm going to talk about what all this leads to as far as mitigation is concerned. So Sarav has already talked about the history. So we started about 4 months ago. Steve, it was initiated by Steve. And so he roped in Jeff Wiles, Sarav, and me. And we started talking about how our knowledge of outdoor dispersion could apply to indoor dispersion. Then we spent a lot of time on it. And then I think Steve got a little impatient about the fact that we were constantly procrastinating and said, okay, let's read some more papers. So he said, well, I'm going to write a blurb for JAMA anyway. You guys can keep on doing what you want to do. And then apparently got involved in looking at aircraft ventilation study with the Harvard School of Public Health. And he's going to talk about that, I presume. Then Jeff and I started having some arguments about some of our work on how it could apply to indoor dispersion. It's not yet finished. At some point, it will get finished. But every time we try to finish the paper, we get some new doubts about our work. So one of these days, it's going to finish. And of course, at every point, Sarav would help us to make sure that the paper was relevant to mitigation. So that all this theory is fine, but how does it apply to mitigation? So Sarav, just wait for some time more. And then last week, or this week, I suppose, yeah, it was last week, we had discussions with Glenn. And then, of course, I wish we had talked to you, Glenn, a little earlier because you provided some insight into relationship between airborne transport and risk of infection. Hopefully, we'll continue with these conversations a little later. So what do I mean by, so as I said, I'm going to confine myself to short-range dispersion. So what does short-range dispersion mean in the outdoor environment? And what I'm going to do is talk about near-surface releases. Short-range usually means in near-source dispersion, that is releases from the surface, when distances are less than the time required to mix the pollutants through the mix layer. Of course, this does not apply to elevated releases because elevated releases are affected almost immediately by the mix layer. And also short range, when I talk about short range, it's also travel time, which is x divided by u is less than the averaging time. So what does that mean in terms of distance? It's about 5 kilometers. So that's basically the type of distance we talk about outdoor dispersion as short range dispersion. Long range dispersion is much beyond 5 kilometers. So, so initially there was a lot of work done on short range dispersion. Again, just to remind the audience, I just want to make sure why my glasses are colored. It's basically I'm looking through from the point of view of outdoor dispersion. So outdoor dispersion at short ranges started way back after the Second World War, or maybe even during the First World War, as Steve tells me, because they had they studied outdoor dispersion because of reasons that I don't want to get into. But as far as dispersion from a formal point of view was developed in 1961, it was based on observations primarily made at prairie grass experiments that was conducted in Nebraska. I don't want to get into the details of the experiment, but essentially it was conducted on flat land with hundreds of SO2 samplers. Sulfur dioxide was actually released. Measurements of metrology were made. Micrometrology was not yet developed at that stage, so the instrumentation was fairly primitive compared to what we have. But it's an amazing set of data. I'm still using it. I think I personally have published about 10 papers on prairie grass because the data set is so well documented and it's a reasonably high quality, maybe high quality because I've written papers on it. But you came up with concentration expressions based on the Gaussian model. By the way, the Gaussian model does not apply for vertical dispersion, but it was convenient to say it applies even to vertical dispersion. Horizontal, it is Gaussian, but definitely not in the vertical. And as some of you might have studied in your classes, these plume spreads, which are sigma z and sigma y, are key to stability classes, A, B, C, D, and F. And they're determined by parameters like incoming solar radiation and wind speed. The unfortunate thing is that it's still taught at universities. This rather ancient way of looking at dispersion is still taught. That's one of the reasons I introduced this. Textbooks haven't changed at all. They have not incorporated some of the recent developments in outdoor dispersion. So this was prairie grass. Then the more recent study is the Idaho Falls tracer study, which was an excellent study that was conducted by the people in Idaho Falls in the NOAA labs at Idaho Falls, led by Dennis Finn. And the nice thing about this experiment was that, of course, it used really good instrumentation, and the release was sulfur hexafluoride. It was designed primarily to look at the effect of barriers on dispersion. But what was nice is there were sulfur hexafluoride was simultaneously released from two sources, side-by-side sources. So they encountered the same metrology. And they were, as you can see on the right of the figure, there were a whole bunch of SF6 monitors, real-time monitors extending to about 180 meters. X divided by H is equal to 30. And the height of the barrier was 6 meters. As you saw, the barrier was essentially made of hay bales. And so this provided an opportunity not only to look at the impact of barriers, but to actually revisit our understanding of dispersion in the outdoor environment, because you had samplers next to each other and you had releases next to each other. But one of the releases was done in the open environment, so you could do the comparison. And concentrations were measured at 56 receptors, and it spanned neutral, unstable, and stable conditions. So this was an excellent database, and it's freely available to anyone who wants to use it. But by this time, micrometrology has also developed, so it was absolutely necessary to make micrometrological measurements. So I think there were about three or four sonic anemometers in front of the release, at the downwind of the barrier. There are a whole bunch of the sonic anemometers that it could be used. But the point I was trying to make here is that you have an experiment, a complete experiment, in the sense that you've got both concentration measurements at the surface, in this case, concentration measurements at the surface, as well as micrometrology. So it led to revisiting the dispersion curves, and the current form of the dispersion curves are here. It expresses sigma z and sigma y in terms of friction velocities, in terms of the Moonin-Obukhov length, and in terms of the distance from the release. So the point I was trying to make is the current understanding of dispersion in the outdoors is closely tied to the flow properties, to the micrometrology. So if you want to predict dispersion, of course, you don't want to go to the A, B, C, D, and E of stability classes. You want to use micrometrology. So the question is, how does all this apply to indoor dispersion? So the first thing we did was, okay, what do we see in terms of short-range dispersion indoors? And I have to, this is basically a paper that was published by some of the who's who in indoor dispersion, pointing out the fact that airborne transmission was very important. And Sarav has already pointed to 2 papers. I think there were umpteen papers, to be precise, on airborne dispersion and why it is important. So what is short-range dispersion indoors? It basically is distances that are less than the length scale of the room. Sarav, I'm not changing the slides. I suppose it doesn't like me lingering on slides too much. But basically, it's distances less than the length scale, and averaging time less than L squared divided by K, which is averaging time less than the time taken for material to go across the room by diffusion. And I'm going to talk about eddy diffusivity and a turbulence velocity scale, because it so happens that a lot of the dispersion indoors is explained by eddy diffusion. And what is eddy diffusion? Eddy diffusion, if you remember, this was a paper that was published by G.I. Taylor, the famous G.I. Taylor, who definitely deserved a Nobel Prize, and I don't think he got a Nobel Prize. This was published in 1921, and he looked at dispersion of a continuous release in a flow with homogeneous turbulence, and he basically looked at plume spread, and he showed that plume spread was proportional to travel time and a turbulent velocity scale, when something called a Lagrangian time scale, which is the length scale divided by the velocity scale. So whenever the time of travel was less than the Lagrangian time scale, the plume spread was proportional to travel time itself. And so which meant that eddy diffusivity was a function of travel time. It was only when the time of travel was much larger than the travel time that you got this square root behavior, which actually translates into constant eddy diffusivity. So the key concept here is the concept of eddy diffusivity is justified only when the relevant distance, which inside the room is of the order of a few meters from a source, is much larger than the turbulence length scale. So the turbulence length scale, that is the dominant eddy scale, has to be much smaller than the distances that we are concerned with. So constant eddy diffusivity that is used often in the indoor environment is justified only when this condition is held. So that's one insight from our current understanding of dispersion. So what I did was, okay, let's look at some of the papers that talk about flow inside rooms. So this was rather important because we wanted to get the same type of information as we got outdoors using micrometeorological instrumentation. So there are several papers actually that do describe flow within rooms or within enclosed spaces. If you notice, the mean velocities inside rooms measured by hot wire anemometers was less than maybe 5 centimeters per second. 5 centimeters, it's order of centimeters per second. So most of the dominant velocities that were measured, so the thing to remember is of the order of few centimeters per second. And the turbulent intensity, which is essentially the turbulent velocity, sigma W or sigma V divided by the mean velocity, is very large. If you notice, it's the order of 30 to 40%, almost 100%. Basically, what it meant was the turbulent velocities are of the same order as the mean wind speed itself, which is rather unusual. This is not true in the outdoor environment, where it's more of the order of 20% at the most. And these measurements did not reveal anything about the dominant length scale. And as I said before, the length scale is just as important as the velocity scale. So then I looked at other measurements. Again, looking for this grand experiment like the Idaho Falls study, the prairie grass experiment that was done outdoors that looked at both concentrations as well as flows. Were there similar measurements indoors? And unfortunately, I was disappointed. I'm sure Glenn was going to correct me. I did not find a single experiment which actually looked the flow field at the same time as concentrations. In fact, we had we were quite obviously not as up on the literature as we would want to be. So we actually had a phone call with someone who had done indoor dispersion, and he said that there wasn't an experiment that combined both concentration measurements with flow measurements. But anyway, there were some good papers that talked about velocities measured inside rooms. Velocities measured by Vasiolek suggested that the velocities range from 1 centimeter per second to 10 centimeters per second. And the air exchange rate was 6 times per hour to 10 times an hour, which is actually large. So with these large exchange rates, you had velocities that didn't go much beyond 10 centimeters per second, and turbulent intensities range from 0.3 to about 0.1, which is of course fairly large compared to what you look at the outdoors. And the spectral analysis, this is one of the few papers that did a spectral analysis of the data. In fact, maybe the only paper. And the turbulent length scale was about 1 to 3 meters, which seems rather odd, which seems too large. So I'd like to look at the spectrum again, because 1 to 3 meters is not consistent with the use of eddy diffusivity. This is a very large, which is a large eddies moving inside the room, is not consistent with eddy diffusion. My feeling is it's more like the order of a few centimeters, the length scale. Then there were papers that actually looked at transport by fitting models to measurements of concentration measured. And one of the papers is Sheff et al., who inferred eddy diffusivity by fitting the eddy diffusion equation with advection to concentrations at several distances from a freon source. And average eddy diffusivity, again, I'm talking about average eddy diffusivity because the default model is actually using eddy diffusivity. So, and the eddy diffusivities were the order of 10 to the power of minus 3 meters per second. So this is a number you need to sort of keep in mind. It's the order of 10 to the power of minus 3 meters per second. And the velocities inside the room were not measured at the same time. That's the point I'm trying to make. When people measured concentrations, they didn't measure velocities. And when velocities were measured, concentrations were not measured. So you didn't have this grand experiment like prairie grass, or you did not have experiments like Idaho Falls experiment. So what I said was, okay, let's look at the best source of information. And this is a paper that was published in Environmental Science and Technology by a group of people from Stanford. And they did these rather nice experiments in 2 rooms. And I show those rooms with a whole bunch of monitors surrounding a CO source. Room one, which was fairly large, which was the length scale was of the order of 5 meters or 6 meters. Another smaller room with a length scale of something like 4 meters. And they had CO monitors at various distances from the source. And those dots you see are the CO monitors. And the ventilation was natural. Natural ventilation ranged from 0.2 to about 5 changes per hour. And the thing to remember is the averaging of the eddy diffusion was of the order of 10 to the power of minus 3 to 10 to the power of minus 2 meters per second, the larger values for high ventilation rates. And what I want to keep in mind is that the averaging time was half an hour. So this was a fairly large averaging time. So all the concentration measurements were made over half an hour. So we reanalyzed the data. Jeff and I reanalyzed the data, but Cheng himself Cheng et al. Have also analyzed the data. So it's worthwhile looking at the paper. But the reason we reanalyzed the paper was we wanted to look at dispersion inside the room using models that actually emphasize the gradients of concentrations. Remember, the default model in most indoor air pollution work is a well-mixed model. They assume that air pollution, as soon as or any material that's released into a room is well mixed in a room. That's the default model. Of course, there are CFD models, which I'm not going to talk about. It's very difficult to justify the use of CFD models when you know so little about the flow inside rooms. But CFD models are used, and they produce pretty pictures, which I don't believe in. But here, what I've basically shown is results from a reanalysis of the data. And the three different plots in the concentration. One is the blue line, which is basically a steady state model, which shows that the concentration falls off as R, that is the distance from the source. And then on the right of the panel, basically this accounts for averaging time. So here is the instantaneous concentration average over half an hour. So this is a fairly long averaging time for indoor air pollution modeling because they assume that it's mixed within the room within a few minutes. And I wanted to find out what happens when you average over half an hour. And the reason I wrote that equation down, it basically has got the error function, is because we struggled a lot to derive that expression. And I'm very proud that we could actually get a nice analytical expression that gave you the concentration as a function of averaging time. And this is compared to the well-mixed model, basically assuming that it's essentially a box model. So if you notice, the scale says concentration divided by C mix. So that is the scaling velocity. And if you notice, the concentration next to the source is about 10 to 20 times larger than the well-mixed concentration close to the source, and then falls off as a function of distance at about 5 meters. But the neat thing to notice here is the concentration never gets really well mixed. The concentration falls off. In fact, it's actually close to the expression on the right, which basically says there is no, the walls have very little effect on the concentration. In fact, it's as if the system is open. The concentration falls off as a function of distance. In fact, is 1 by R. And it's governed by the eddy diffusivity. And the figure on the right basically tells you that the concentration, the concentrations actually, even when the air exchange rate is as high as 1.25 per hour, the concentration pattern shows no effect of the walls. In fact, it basically says, I don't care what the walls are. I'm not going to get well mixed. I'm essentially going to assume it's an open system. So this is the point I was trying to make, is that there is a gradient, and this gradient really doesn't care about the room when the room is about 5 meters. But when the room is about 3 meters, the length scale is 3 meters, the walls start making a difference. Here again, you see there's a gradient. And in principle, at these high air exchange rates, the walls should become very important. But even here, there is a gradient. If you notice in room 2, experiment 5, you see that the concentration actually starts seeing the wall. The wall says, okay, here I'm going to be important. But the main point I was trying to make here is that there is a gradient, and assuming it's well mixed is not always a good assumption. It might be a good assumption during certain times. This also basically means that multi-box models are also, should be used with a lot of caution. So I think basically what I'm saying is that concentrations have gradients, and they can be predicted using an eddy diffusivity. An eddy diffusivity that depends on the ventilation rate. So the point, this is, by the way, Cheng has also done some of this analysis. We have reanalyzed his data. So here you find that we estimated the eddy diffusivity by fitting a steady state model to the concentration measured at the closest distance, which was 0.25 meters. And on the y-axis is basically the eddy diffusivity inferred from the ventilation rate, and there's a very high degree of correlation. So if you notice in both cases, room 1 and room 2, there's a high degree of correlation between the eddy diffusivity inferred by fitting the concentration to the data and the eddy diffusivity associated with the ventilation rate. Tau here is the ventilation rate. So the point I'm trying to make is that when you measure the ventilation rate, you're essentially measuring the eddy diffusivity that you want to use in a model. And apparently, you can actually predict the ventilation rate in rooms. So basically, that's fairly encouraging in the sense that you can actually predict eddy diffusivity. And it appears that wall effects become important when the air exchange rate is greater than 2 per hour. So there are wall effects and well-mixed effects. If you notice, the plot on the right shows that the spatial mean approaches the well-mixed concentration when the air exchange rate is about greater than 2 to 3 per hour. But that, of course, depends on the details of the ventilation rate. So the major point I wanted to make here is that assuming it's well mixed is not a good assumption in some cases. Here I'm sort of hedging my bets. I'm going to have Glenn argue with me about this, but that's basically my view, that we need to account for gradients in looking at concentrations. So I'm going to say a few words about puff dispersion. As I said before, I'm going to look at dispersion only when you're not coughing and sneezing. This is dispersion of puffs that are coming out of a mask. But this is when somebody's speaking or talking, you have still stuff coming out, and they come out in terms of puffs. I don't want to get into details of how puff dispersion occurs, but the main point I want to make is that when a puff is dispersed, it's sort of stretched by turbulence. Turbulence essentially takes that the initial thing and sort of stretches it all over the place. And within these strands, the picture you need to think about is a ball of wool. So you have this ball, and as the turbulence acts on it, it sort of stretches this into strands. And molecular diffusion becomes important when these strands become as thin as the Kolmogorov scale. And the dominant length scale and the Kolmogorov scale are dependent on the Reynolds number. So the point I was trying to make is the Reynolds number is fairly small inside a room. It's fairly small inside the room. So the Kolmogorov scale can be of the order of 1 centimeter inside the room. So your puffs better be much bigger than a 1 centimeter for it to be stretched. So if the puff is actually smaller than the Kolmogorov scale, the puff doesn't spread much. It actually remains intact, and you're going to get a big blast of that puff. So in order for dispersion to occur, you want to make sure your initial puff is much larger than the Kolmogorov scale. So the turbulence has got a chance to actually spread it. So so here you see in the picture, the scale is fairly large. So wear a mask. Wear a mask not only to reduce the concentration at the source, but to stretch this puff. So if the puff is fairly large, turbulence has got a chance to actually stretch it and disperse it. And so the puff dispersion has got its own theory. I don't want to go into its detail, but what happens is when there's sufficient time, it starts behaving as square root of time. That is, essentially, it spreads the square root of time, and you can use a constant diffusivity. So I'm not going to go into details of these calculations. It's going to bore, but what I'm going to emphasize is the dose depends on, of course, the emission rate. And it depends. And in terms of if the motion of the puff is random, if it's basically the puff is sort of in a naturally ventilated room, and the puff is sort of moving randomly all over the place, the dose actually falls off as 1 by r squared. That is, as you go far away from the source, it falls off as 1 by r squared. The situation is very different when it's a plume that is in a ventilated room that has got ventilated using some mechanical means. The dose actually falls off as 1 by r. So it falls off much slower if you're inside a room that is ventilated mechanically. And I'll explain that because dose and concentrations fall as 1 by r, but they're also directed. They're directed from, say, the inlet and the outlet of the ventilation system. So the point here is in a naturally ventilated room, it falls off as 1 by r squared. In a mechanically ventilated room where you have flow that is induced by the ventilation, the dose actually falls off as 1 by r. And the question is, why am I suddenly talking about dose rather than concentration? Because it's dose that matters. As Glenn will show you, it is dose that matters. Basically, the number of what I call virons. I think virons you inhale when the puff sort of goes past you. So what are the implications of all this? In an environment which the mean flow is not organized, the dose varies as 1 by r squared, where r is the distance from the source. The mixing occurs in all directions relative to the source. So that's a disadvantage. The point is, even though the dose falls off rapidly, it appears all over the place. So you can't escape the dose. So it basically says that if you're inside a naturally ventilated room and the ventilation is poor, if you stay in that room long enough, you're going to be exposed. And this is what seems to have happened in a poorly ventilated church in Skagit County in Washington in March 2020. Glenn is going to talk a little more about it. Something like 80% of the people who attended this choir practice got infected. They stayed in this poorly ventilated room, which basically meant that any sort of emissions was sort of spread all over the room. So what happens when ventilation is mechanically forced? So the peak dose decreases as 1 by r, but it's directed, which basically means that most of the room is not exposed to the dose. But if you're in the path of the flow, you're going to be exposed to it. So the time spent is less important. Less important if the receptor is located upwind of the source, as pointed out by Lou, who this was basically a situation in a Chinese restaurant in China, obviously, where people were sitting together in a room. 3 families were sitting in the room, and they were sort of blasted by this air flowing past them from an air conditioner outlet to an exhaust. And because they were in the path, a lot of the families got infected. In fact, among 10 people belonging to 3 families were infected. And as I said, it induced flow, a strong flow in a certain direction. And what happened was that nobody else got infected. Even the waiters didn't get infected. It's only these 3 families in the flow, in the path of the air, got infected. So basically, there are qualitative differences between natural ventilation and mechanical ventilation. So this leads me to my last slide, which is mitigation, which is rather obvious. The risk of infection. Again, Sarav, this is responding to your questions. Ventilation, which induces transport. So increased ventilation, that increases eddy diffusivity. Does it mean that we should avoid organized flow to mitigate high doses? This is a question mark. I'm not even sure. Do you want to have flow that is organized? Because it might expose people to high doses. And increasing source size at the source, so a source size at the source, which basically means wear a mask or something that increases the size of the source, will accelerate the spread of the puff because it allows turbulence to stretch the puff all over the place. Of course, increasing distance from the potential source of infection is very important. There's no such thing as a safe distance, 2 meters or 3 meters. If you stay long enough in a naturally ventilated room, you're going to get infected. Doesn't matter. Distance really does not matter. And of course, decreasing time spent. Time spent is also important because eventually it's dose that matters. Both time and space are important. And so I'm going to end the slide with the research needs that he talked about, Sarav asked me to talk about. We need a room study. We always have these really nice field studies in the outdoor environment. We need a room study that measures both concentrations and flow, as in the Idaho Falls field study. That is, we should have continuous and tough releases of tracer, at time and space resolved concentration measurements using PIDs, using continuous monitors, using a whole bunch of instrumentation. In addition, we need time and space resolved velocity measurements with sonic anemometers, hot wire anemometers. And of course, it should be accompanied by visualization with colored gases, not with smoke, but with colored gases. So basically, I think if you have this sort of information, we might be able to say a little more about indoor dispersion. And this is the bibliography that I quoted. And that's the end of my talk, Sarav.
Thank you, Venki. That was very enlightening and engaging with the background, going back to dispersion theory. We are a few minutes over in terms of where we wanted to be. So in the interest of time, I'm going to request the audience to submit their questions through the Q&A widget. And then Venki, if you would please monitor that on the side and able to respond to that in a written fashion. But we will come back to the entire panel at the end after both Steve Hanna and Glenn Morrison go through their talks, if you want to have some more oral responses to the questions. With that, let's transition to the next speaker, Professor Steve Hanna. Dr. Steve Hanna is an adjunct associate professor with the Exposure, Epidemiology and Risk Program at the Department of Environmental Health in the Harvard T.H. Chan School of Public Health. Dr. Hanna is a specialist in atmospheric turbulence and dispersion and in the development, evaluation, and application of air quality models. He's a fellow of the American Meteorological Society and is currently part of an HSPH study regarding guidance for reducing risk of COVID-19 in indoor environments. Steve? You're muted, Steve.
Okay, thank you. I'm technologically challenged here, so I was incapable of sharing my screen, and Sarav is going to be controlling the slides. So Venki already covered a lot of material, which, you know, I was going to mention, so I'll be able to pass over some of those things myself. But the main purpose of this talk, yeah, I'm not really talking about mitigation or the initial aerosol releases or anything. I'm just strictly talking about the dispersion, transport and dispersion. And I'm going to be giving an overview of several alternate models like the multibox, CFD, Gaussian plume puff, and K-theory. Next slide. And Sarav already mentioned that there is this study at Harvard School of Public Health about airlines, guidance for airlines in order to mitigate COVID spread. Next slide. So I think it's fairly obvious, and from the slides Venki showed in Sarav's introduction, and you're certainly going to hear from Glenn later about most of these, but there's actually several components to the comprehensive modeling system. And I really don't know much about most of them, but I do know something about transport and dispersion modeling, so that a topic in the middle is the one I'm going to be discussing. And as Venki said, he is treating it as basically a discussion of an inert tracer. So the idea is if we can model the inert tracer dispersion and get concentrations and doses right, then they can add, somebody else can add aerosol evaporation and other things to it. Next slide. So let's start with outdoor. And I was concerned, you know, with both outdoor and indoor. And one of the reasons I was concerned about outdoor is a few months ago, several experts were saying, well, if you're outside, you don't need to worry at all because it just gets blown away. And I thought, really? It doesn't just get blown away. We know what dispersion is. So outside we have, as Venki mentioned, like Gaussian puff or plume models. There's Lagrangian particle models many people have. And then there's several classes of Eulerian models, which are solving the basic diffusion equation and equations of motion and so on. There's the K-theory approach, which I think is what Venki was spending most of his time on. And then even at the larger scale, there's the regional models like CMAS driven by WRF. And I believe I'm right when I say that both are actually large eddy simulation CFD models, but they have fairly large horizontal grid sizes, you know, several kilometers, as opposed to the usual LES RAN CFD models that are applied to smaller grids. Next slide. Okay, so all those outdoor models are also applicable indoor because it's still the atmosphere and you still need to know the airflow, the mean airflow and the turbulence. But there's a whole nother class of model that is widely used indoors, and these are first of all well-mixed room models such as Contam, and you can also apply Contam, or they've developed it so that you can handle a building with multiple floors and multiple rooms, and you need to know the HVAC system characteristics, flows out of vents, air change rate, and so on, the air that's going to go through the door from one room to another, and then you are able to solve the indoor concentration. But then there's another model that we use a lot at Harvard School of Public Health, and it's called, well, I'm sorry, I haven't got to that next. The next slide. Well, no, let's go back to the previous slide. It is that last thing. So the multiple room model has been downsized to multiple boxes. So it's a multiple box or multiple zone without boundaries inside a room. So for example, the way they do it with to model what's going on inside an airplane is a box is drawn around each passenger, and that represents a zone or a box, even though there's not a hard boundary between one box and the other, like between you sitting in one seat and your neighbor. It still is treated as like a grid box with fluxes going from one to the other. Next slide. As I said, this is all for conserved tracers, and there's a whole other areas where hundreds of people are working on it now, on aerosols, evaporation and deposition. And what happens if the aerosol quickly evaporates and it forms a solid particle, maybe with one or more virons on it. And the other thing that there doesn't seem to be a real agreement on is the viron death or decay with time. And if you know that, you can use a half-life approach as we do in radiological models. Next slide. And Venki was getting into this when he was talking about doses. And I find also, at least my interactions with the Harvard epidemiologists and experts, that there isn't a great agreement on the number of virons that can cause someone to get a COVID-19 infection. You know, is it a few hundred or less or more? And also, are you able to get those virons just in a couple of seconds as a sneeze puff goes by you? So if you inhale that, you know, that's just a short-term concentration rather than a dose. But if it requires a lot of them and a lot of time, then, you know, it may be that you have to be exposed for an hour or so. So the dose duration is very important. And the last thing which I'm finding in the Harvard study is that their endpoint of the calculation is a risk to the entire population that's in the room or the structure or the airline cabin, which means you have to integrate over all people and all times. And that's different than, say, if you trying to determine a worst case risk to a single person sitting 1 meter from the person who sneezes right towards you. Next slide. So I went a slightly different way than Venki, who he and Jeff are using the diffusivity, the K model. I'm using a near field model for instantaneous puffs or plumes that I've been using quite a bit lately for urban dispersion model comparisons, for dense gas model comparisons, where there are multiple other much more complex models being used. And what I find is when you actually compare it with the observed data, the tracer concentrations, the simplified model generally occurs just or performs just as well, at least from a statistical viewpoint, as many of the more complex models. And one of the reasons for this is there's so much variability in the atmosphere, that the white noise variability basically makes it so it's hard to show that one model is doing a lot better than another model. So what you need for this is a source term. You always need that for any dispersion model or effects calculation. And I often find that, by the way, when I'm interacting with a lawyer, the first time he calls me about a case, says, yeah, can you model this? And I say, yeah, sure, I can model it. What's the source term? And then they say, what do you mean? And so then you have to explain, well, we can't do anything unless we know the source term because the accuracy is proportional to that. So you really need to know that source term. The fourth thing is the initial cloud size at the source. And Venki showed some pictures where an artist shows the material, the aerosols covering a volume that's about 1/2 meter in diameter. And is that what it is? The next to last, you need to know the flow speed. That's the mean flow speed for a continuous release. And then you can calculate the concentration downwind. Next slide. So let's first look at a continuous plume. And I'm just going to take a couple of slides and go through this example because it's really simple and you can write it analytically. And we know from looking at a lot of data, and you can also use some theory about turbulence intensities, that the diameter or the spread, the lateral spread of a cloud is increasing with distance as about, say, 0.1 or 0.2 times the distance. But then you assume an initial size to the cloud, and I'm making a very simple assumption that the size d at any distance equals the initial size plus 0.2x. And then you end up with that formula in bullet 3, where you see the concentration is varying as 1 over x squared. And as Venki pointed out, if you integrate over all time, the dose is proportional to 1 over x. But I'm just looking at the maximum concentration. But then one of the things is that the ratios that the Harvard School is interested in is the ratio of concentration at one distance to the concentration at the source. And with this model, it just comes out simple, the square of the initial size divided by the square of whatever the size is at a distance x. And with this, and I'm assuming for, say, a breathing person, the initial diameter is 0.2 meters. I didn't mean a breathing person. That implies he's alive or not. I meant for a breath from a person is maybe, I'm just guessing, 0.2 meter size. And so you get the concentration drop off by a factor of 4 between the source and 1 meter, and another factor of 10 or so going out to 5 meters. And this seems to be something that the epidemiologists are really interested in. Next slide. Now switching to a puff, and Venki covered this too, that then concentration is inversely proportional to distance cubed. And now I'm assuming, since it's a puff, that it's a sneeze or a big cough or something. And then the initial diameter, I'm just guessing, is 0.5 meter. And now you then also get ratios of concentrations at 1 meter to source here of 0.36, and it drops off another factor of 10 out to 5 meters. So this gives you some useful information. Next slide. Okay, and this has always puzzled me over the past few years. When I look at the indoor dispersion modeling, it's like I'm in a different universe than what we do in outside modeling. And they have proceeded on somewhat independent paths, that is calculations of turbulence and dispersion. The exception is CFD modeling, where and there's CFD models being heavily used outdoors and also indoors. And in some cases, it's the same people. So, you know, they're applying it both places. You still have this turbulence closure assumption that needs to be carefully defined indoors. Then there's the multi-box model, which is preferred by Harvard School of Public Health people I'm working with. They are using this model by Noakes et al. And Jones et al., both of them from 2009. And it applies to a well-mixed box that's applied to several boxes or volumes in a room. And in the case of what they're doing here, as I mentioned earlier, it's boxes that are around a passenger on a plane. And one reason they're using this is because it's not just the transport dispersion model, but this model also has the whole risk consequence and the Monte Carlo uncertainty built into it. So actually the transport dispersion is just one part of this total model system. And they'd prefer to use that. All models, however, in this list need the mean flow and the turbulent velocity to be parameterized. Next slide. So here's what happens in the multi-box. I think I finally figured this out after I reviewed the papers. There's a mass consistent condition applied to each box, and the terms actually are very similar to those in K theory. The problem is that instead of using the full K theory formulation for the turbulent flux, and actually it's the second derivative of the concentration, is that what they're using only has the term sigma u, which is the standard deviation of velocity, and does not really use a K formulation. So I said, well, okay, if you guys insist on using a multi-box model, the way to fix it is to multiply the sigma u by the turbulence length scale divided by the box size. And actually, Venki discussed turbulence length scales a lot in rooms and so on. There's questions about what it is. In the airplane, I say in a room here, but in the airplane, the length scale is about 1/2 times the room dimension, because there's a big double vortex ventilation system within an airplane. And still the turbulent velocity needs to be known. Next slide. And Venki already covered this really. We have a lot of data for outdoor models. He mentioned prairie grass. Some data are available for well-mixed room models, fewer available for near field models, although Venki mentioned 2 or 3 papers that do contain some data, but they don't really all take simultaneous flow data. So what I'm going to discuss below is 2 indoor tracer data sets. So next slide. Okay, Venki mentioned that we had talked to Mike Sohn at Lawrence Berkeley Lab, and he does a lot of indoor experiments, and I've worked with him on several joint field studies. So he said, as Venki mentioned, there really isn't any good data set with near field dispersion measured inside and also flow. So he got some money from somewhere to do this. And this is a description of his experiment, which is being done in his laboratory at Berkeley Lab. So he has a single room, various ventilation strategies are tested. He's using CO2 and aerosols, and they're releasing them simultaneously from a mannequin. And he says, hang about 20 CO2 sensors. And by hang, I think he means that literally you hang it on a wire or a string or something from the ceiling. And you also hang hot wire anemometers or other anemometers. And these experiments are underway now. And we hope to have those data to be able to test and further develop our indoor near field models in a few months. Next slide. Now this is the Transcom tracer experiment, which recently got a lot of viewing on the TV. And I will show one of the next slide actually will show. This is from the Today program on 15 October. And Hoda gave a little thing about this study. Okay, can you go up to the previous slide again? Okay, so this report was just released, and it was done by the Transcom, which is the military organization that flies servicemen all around where they need to go. And they had the same problems as the commercial airlines. So they co-sponsored this study along with DARPA, Defense Advanced Research Project Agency, and co-sponsored by Boeing and several other groups. Boeing supplied the jets. So here's a picture. Well, this is the boss and one of the technicians, I guess. And now you can see the experiment. You see the mannequin's head there. I guess I was told they didn't have enough money to buy 200 mannequins to put in the cabin. So I ended up with a head. And the head is also used they put masks on the head, and they also had some receptor locations with mannequin heads with masks on. And you can see the sampling devices as the little vertical poles with what looks like a cup turned upside down on the top at each seat. So they're sampling at each seat, and there's a source at each seat. Now can you go 2 slides down? Okay, it just took place in late August, and because they use the 767 and 777 a lot, that's what they studied. And they talk about the heads of mannequins, and what was released was fluorescent tracer particles. And these were small plastic beads of size 1 to 3 microns. So they really don't settle. And they released about 100 million of these in each tracer study. And they were released for 2 to 4 minutes during a combination of ground. There were some experiments on the ground and some in flight, all with ventilation systems operating. There were about 40 sensors, and with resolution of the concentrations was 1 second, and multiple rows for forward, forward, mid, aft, and aft. And because some of us have been complaining that they should have had mannequins in the seats because the mannequins actually are obstacles to the flow. So in a real airplane, you have hundreds of obstacles to the flow that are affecting the flow and turbulence, but they didn't. But they did represent the heat emitted by passengers by a heat blanket on each seat back. Next slide. As Venki said, a typical building or room air exchange rate is 1 to 5 or 10 per hour. The airplane, they can get up to 30 per hour. It's also HEPA filters are used, and half of the air that's going through the system is replaced by outside air each time around. Mean flow velocities were measured by Boeing of about 20 centimeter per second and turbulence of about 8 centimeter per second. So in a minute, a puff can travel about 12 meters and disperse crosswind about 4.8 meters. So near field dispersion is important. Next slide. And here's some results. The masks, they found that mask worn continuously can greatly reduce risk. And this is one of the firmest recommendations it's made. And they're making these recommendations to the entire airline industry. High air exchange rates and HEPA filters are definitely good. And obviously clean air being mixed is good. And also the high ventilation rate should really be continued at boarding and deplaning, which isn't what their aircrafts were doing earlier. Next slide. So here's some near field results of this study. And they use doses expressed as fraction of total number of beads. And for example, at the bottom, I give a typical, there's a lot of figures shown in the report that right at the source seat, obviously there's 100% of the beads emitted. However, at the adjacent seat, the dose is only 0.05% of the total number of beads. And then it doesn't drop that much more at the next seat or the next seat, you know, just by factor of 2 or so, which and Venki kind of implied this would happen too. The next slide. So the observed doses vary by a factor of about 10. However, the Transcom report and a big deal made in the TV reporting was that doses drop off by 99.99% at the next seat location. But personally, I think that somehow that wasn't calculated right. And you should be looking at the initial concentration in the initial cloud. And when you do that, the concentrations don't decrease with distance nearly as much. Next slide. So the next additional guidance, this is only one part of the modeling system. And this is just a motherhood statement. High ventilation mass wearing distancy during the entire scenario. And is there another one, Sarav? I'm not sure.
I think that's it, Steve.
Okay, that's it. So that's, thank you.
Thank you, Steve. That was great. In the interest of time, let's keep moving to the third panelist. I want to make sure that Glenn has his time to go over his slides. And then hopefully the audience can stay a little bit longer to have some discussion after Glenn's comments. Glenn?
Thank you.
Glenn, just a second. Yeah, let me.
Yeah.
Yeah. Okay. Dr. Glenn Morrison is a professor in the UNC Department of Environmental Sciences and Engineering. He's a fellow and past president of the International Society of Indoor Air Quality and Climate. His research encompasses indoor chemistry, physics, aerosols, materials, and exposure. He and his UNC colleagues are currently studying the airborne transmission of SARS-CoV-2 in patient residences, in lab experiments, and via modeling. Go ahead, Glenn.
All right, thanks. I turned off my video just to make sure that my not so great internet at home doesn't break down. And you can see my slides okay?
Yeah, very good.
Okay, great. So in the interest of time, I'll move forward pretty quickly. I wanted to make the point that, and many of you have noticed, I'm sure, in the news that this aerosol question has been in the news, but it seems like public health bodies haven't really been accepting the idea of aerosols, despite quite a bit of evidence for aerosol transmission of COVID. If you haven't noticed, this has changed just recently. So earlier this month, the CDC acknowledges aerosols as a method of transmission, means of transmission, and an important one. And until today, the World Health Organization had not. And just today, they put out a video recommending ventilation, which is implying that they're accepting that aerosols are part of the puzzle. So it's taken a very long time for this to happen, despite the evidence. And Venki and Steve alluded to some of that evidence. I wanted to mention some of it very quickly. So big picture, the super spreader events are far, far more likely to occur indoors and outdoors. This is indirect evidence of aerosol transmission just by itself. The dinner in China that Venki mentioned is, there's an image of that here, in which by looking at the flow in these buildings, in this building, they could tell that aerosol transmission was the most probable way that people got sick. And then of course, the Skagit Valley Choir incident that's been commented on several times. There's these nice epidemiological sort of event-based evidence for aerosol transmission out there, and there's many more. But there's also evidence that the live viable virus can be aerosolized from the respiratory tract, and that it is present in the air of rooms of patients. And further, this just came out this week, the virus can be transmitted from one ferret. Ferrets happen to be quite susceptible to this particular virus. It can be transmitted by aerosols from one ferret to another ferret in a chamber that has the virus. And so in this case, they ensured that it wasn't droplet transmission or some other transmission mechanism. So we have a very clear, I think, set of evidence from many different directions that say aerosols are at least one of the ways that this virus is being spread. And so if that is the case, that means that we have the ability, as Venki and Steve have mentioned, to look at this as an airborne aerosol, and that we know how to deal with aerosols and how to assess exposure to aerosols. But we need to add one layer to that, and that is the ability of people to actually acquire the virus and become infected. And there are a set of equations that were developed since the early part of the 20th century called Wells-Riley equations, which describe the infection of somebody by the aerosol route inside buildings. And that probability of infection is given by that equation there. This N value is a number of quanta. Venki and Steve mentioned the virus and virons. These are words that are kind of used, but quanta is a value that is a recursively derived, generally recursively derived value that says that, well, in a typical event, it's the amount inhaled in order for roughly 63% of people to go infected. And it doesn't specify the number of viruses. It doesn't specify how they were breathed in. It's just a way of determining. And so if you can calculate the quanta emission rate, then you can get to risk later on. There are other ways to get at quanta, and I'll mention that in a moment. But if we know something about this quanta emission rate, we can start getting at dose. And from an exposure perspective, we just use a traditional methods of determining dose by inhalation rate multiplied by the number of exposure events. There may be a moderating factor of masks, and then the integrated concentration that you're exposed to over time in your breathing zone. That integrated concentration, we can go to very complicated and perhaps apt models, as Steve and Venki have mentioned, or CFD models. But from a simple public health perspective, the well-mixed box model works extraordinarily well for exposure assessment. And so we can calculate that risk by determining the concentration in a space, the time-dependent concentration, from just a simple mass balance on a room or space assumed to be a well-mixed box. And you can see all of the parameters there, and most of you should be quite familiar with this. We can solve that equation and then drop that equation, that result, into our number of quanta inhaled. So now we have a dose for a particular event. And when we do that, we get a kind of messy equation that looks like this, and but what's nice about this equation is that we have a few simple dimensionless parameters. This one in red is a dimensionless exposure intensity. That's what I'm calling it for now. We have a dimensionless time parameter, and then we have this kind of dimensionless exposure initial condition, which I'm going to actually drop out in a minute. But that means that you have this colorful little equation for the dose that is much simpler and something that can help us visualize events or a gathering, and to get at risk in a sort of a simple visual way. This equation, we can use the general case, but I like to look at these two cases that are on the bottom here. One is the periodic case where you come into a space that is otherwise been aired out, like you go to a classroom that hasn't been used for an hour or so. In that case, there's no initial condition, there's no initial virons in the room, and what you're breathing in is associated with this time, this rise in concentration of quanta in the room over time. If you have a quasi-steady state system, you can use the bottom equation, and this is has more to do with risk across the population, because you're assuming sort of an average low level of infections people on a let's say on a bus, and you get on and off the bus, there's always people on the bus. But there are other situations that you can use that equation for. So in visualizing this, you can put this on a nice figure that looks like this, where your risk of an infection from one or more events is given by these kind of isoplex-like lines, where B is this dimensionless exposure intensity, which includes things like the quanta emission rate from a person, the number of infectious people present, your inhalation rate, all of those parameters. Then on the x-axis is our dimensionless time. As you move up up one of these lines, you're actually increasing. This is actually the true time axis for a figure like this. And if you can calculate all of those parameters, then you can put yourself on this as some dot on this plot and see what your risk is. This is for the intermittent exposure case, and this one here is for this continuous exposure case. So we can, I've been using these this type of figure and these kinds of calculations in discussions with the Department of Transportation, and how they are preparing, how they've been trying to prepare buses to be as safe as possible for passengers and for drivers. But in order to do that, we need inputs to these models. And so the thing is, we have a lot of really good information about most of the parameters that we need to use. For example, we have inhalation rates for very detailed inhalation rates for people. We know a lot about mask efficiencies now. We know a lot about air exchange rates. So all of that information we have. The more uncertain parameters have to do with the virus itself, like quanta emission rates. And so that's each of these parameters we have now. We have OK measures of these. And so I'm just going to talk about the quanta emission rates for just a moment, because it's important in telling us how well these models really work. So Buonanno looked at the amount of viruses that had been reported in the respiratory fluid of people. So there's enough really good information out there on this. And also knowing how much of that is actually active and that can replicate. Then they took their measurements of the amount of this fluid that is actually released when you breathe and when you cough and when you speak as aerosols into the air. And from that, they could calculate a quanta emission rate, which you can put into something like the Wells-Riley equations. What they get are values that range from about 10 to 1,000, give or take, depending on your condition. So that's a nice sort of bottom up. Let's look at what's in the respiratory tract to figure out what people are releasing. But we can also do it the reverse way, which is actually the more traditional way, is we can use the model to estimate the quanta emission rate if we know something about a spreading event. So we can take an event, find out how many people got sick, and then use that information to back calculate the quanta emission rate, as long as it's a well parameterized event. That was the case in the Skagit Valley Choir situation, where it was a not well ventilated building, and people were singing, and they were able to back calculate the quantum emission rate of 1,000, assuming a well-mixed box model, a box for this church, and actually, which was probably a pretty good estimate. And so that's just one. I've done several of these. There's not that many, there's many events that have been reported, but not that many where you have enough information to actually calculate quantum emission rates. But for the ones that I've been able to get, it's pretty consistent. So for example, this is a bus, and we know something about how buses operate. We know the type of bus. We know how many people got infected. We know how many people were there, for example. And from all of that, you can put in the parameters that you know, the ones that you know with some uncertainty, and get a range of quantum emission rates. And for this one, it came out to be between 100 and 300, which is itself consistent with the Buonanno results and with the Miller results and others that we've done. So the idea that, and this is all built on the assumption of a well-mixed box, which is kind of simple and nice, especially from a public health perspective. So we have this intermediate observation that the Wells-Riley model actually works pretty well. And we can now, I think, use this in a broader sense to ask, what is this telling us about what we can do with to make recommendations? The recommendations that we can make now from something like this is basically everything we already recommend. There's nothing new here. For example, using this visualization, let's say you're a passenger who is riding a bus every day for 6 months. Back in the early days of the, let's say in March of the pandemic, your base case risk would be about here based on my calculations. And that's because you're not going to be exposed every time you're on the bus. You're just going to be exposed periodically. And one of those exposures would rise to the level of being enough to make you sick. But if you start adding on public health measures like reducing the occupancy of the bus, increasing ventilation, decrease trip time, or add masking, now you've layered on these public health measures that each one give you what's interesting is almost a very similar reduction in risk on a percentage scale. And so you end up with roughly almost a factor of 100 reduction in risk by layering these, but no one of them is probably sufficient. And that tells us kind of what we kind of expect, I think, if it is airborne. We can apply this approach to the population as a whole. And the way we do that is to, if we assume that aerosol transmission dominates, we can take the probability distribution of all the input parameters that we have in an equation like this, like air exchange rates, breathing rates, how long you're present at an event, how many events there are that you're present at, all of those kinds of things. And use in a stochastic way, sample from those distributions to calculate the magnitude and distribution of infections that result from going to some event. So when I say gatherings, we're talking about anything that you're indoors at. It could be going to the grocery store, but it could be going to a church gathering. It can be a rally. It could be anything. And it could be just a couple of people having dinner together. So the probability distributions that we can call from, there's actually a lot of information on these. We can actually go out and say, oh, what's the probability distribution for air exchange rates in residential buildings and commercial buildings, et cetera, and build a distribution that we can sample from for a Monte Carlo analysis. So that's what we did here. And there's different distributions for each parameter, depending on what we can find in the literature. Some are more certain than others. And doing that, we can build up we run the model, sample from these distributions, run the model, and get a number of people infected. And we do that over and over and over. And when we do that over and over and over, we get something like this for 100,000 gatherings. And it looks like a forest of infections. These are the number infected at a particular event. Some are very, very high numbers and some are very low. But in reality, there's a lot of blank space between those trees and that forest of infections because the lines are too thick. And so what we can do better is to sort that and push everything over to the right. So the highest are on the right and the lowest are on the left. And when you do that, you see that you get a very highly skewed distribution of infections. And the over 80% of the gatherings result in no infections at all, even if there are infectors there. And 5% of the gatherings are responsible for 80% of the infections. Now, this is a kind of unique and interesting result. And what you can say, well, I ask, is this consistent with what we see in the epidemiology of real super spreader events or any spreading event when you look at them as a whole? And indeed, that is the case. Most people become sick. Most people that are sick become sick during super spreader events, I should say. And we can visualize that by looking at databases that have collected together spreading events. They're not complete. The comparison is not exactly an apples to apples comparison for a number of reasons, but it's the shape of these curves are the same. And we can actually look at this even more quantitatively and ask, is the skewedness, are the number of people that are being sickened relative to the number of events similar to what we see in this pandemic, early in the pandemic, before we start applying public health measures? And in fact, this is the case. Our model shows something like 24% of infectors cause 80% of infections, whereas we see a typical report is something like 20% of cases are responsible for 80% of local transmission in the population as a whole. And so that's just one way of looking at it. This isn't a slam dunk, certainly. But we can also look at the reproduction number, which is the number of people infected per infector. And you can see here that this ranges from about 1.5 to 4. We get a number of about 3, which is we have more confidence that the model is a reasonable representation of the transmission. And here's another way of looking at it. It's called the dispersion number. The dispersion number or over dispersion number, sometimes it's called that, is around 0.1 in the population. We have about 0.2 in our model. Not that different, a little bit different, but ours is within the range of what you see in the literature. So what can we do with this information? Well, we can ask about mitigation. Okay, so what I expect masks to do if we apply universal masking, but let's say only 90% of people actually adhere to universal masking. Well, interestingly, you still see super spreader events. That is going to happen, even with masks, if you do nothing else. But you reduce the number of cases by 75%, and your effective reproduction rate drops below 1. I could put other examples, but for the sake of time, I'm just going to summarize that on the whole, assuming a box model and using inputs that we understand and the distributions of inputs like air exchange rates in buildings actually gives us results that are pretty consistent with what we see in the literature, not just in single events, but also across the population. There are a lot of caveats, and I have some of them here. Some of the caveats are simply that we don't include the kinds of more complex exposures that occur as described by Venki and Steve. But even so, I'm not sure that's necessary when you're looking at it from this level. So I want a few shout outs to some people, some of the aerosol activists, Barb Turpin at UNC and the SARS-CoV team. And I'll leave it there, leaving 0 minutes for questions.
Thank you, Glenn. That was great. Apologies to the audience for running a little bit behind, but I think that was a delightful panel with a lot of very good information on the topic of this particular panel. If I may indulge the panel and the audience to take a few more minutes for some discussion and questions. Venki, there's one question from Richard Monteith on the Q&A panel. Does changing airflow source indoor or outdoor help eddy dissipation rate? Venki or Steve or Glenn, would you like to respond to that?
Yeah, any increase in flow should increase the dissipation rate, especially if the length scales are small, because the dissipation rate depends on the turbulent velocity cubed divided by the length scale. So the point is, I'm not sure what motivates that question by itself. But I assume that the turbulent dissipation rate being high will also help to disperse a puff, because if the scales are small, the dissipation rate is also going to be small. It's going to be large rather, and you're going to be able to stretch the puff much more under those conditions. But as I said, directed flow might have some adverse effects. That is, you're in the path of the flow, there could be a problem. But I'll allow other people to answer the question, but it seems like that super spreader event, or it's not the super spreader event, it was actually an event where a few people got infected in the Chinese restaurant where they were in the path of the flow, is something where the ventilation rate was high, but it caused some problems for a few people sitting there, and perhaps high doses.
I would say that in that case, in that zone, that was a super spreader event. If you consider it on a percentage basis, so in that little well-mixed zone, a lot of people got sick relative to the number of people that were there.
If you insist on the word well-mixed, Glenn, I will.
Well, it's not a well-mixed. I'll say in that zone in which people were exposed to that recirculated air, right? I mean, it was clearly. We could not to quibble about that, but. Having a large number of people at an event relative to the number that are there can be considered a super spreader event.
Okay.
I want to come back to the well-mixed in a second, but before that, I have another question from Tesh Rao. Great talks on dispersion public health work. I have rather simplistic questions when talking about mask efficiency. All different types of masks considered to be equally protective, and given that we are in the cusp of the fall season, is there any definite evidence on how weather affects C19 transmission and dispersion?
One is certainly is know that the mask efficiency varies quite a bit, but on average, a typical cloth mask has a certain range of efficiencies which we can put in models and integrate them into that analysis. Right now, there's no definitive evidence on how weather affects it. There is some evidence that it is more viable in drier conditions, but that's right. That's true of many viruses, and so it's unclear. Yeah.
Well, one way the weather affects it is it makes us all go inside instead of outside.
Well, it depends on where you are, right? I mean, in the South, when it's really hot during the summer, you actually spend more time outside in the winter.
Well, I'm in Maine right now and it's 28 degrees.
Yeah, so it really is location dependent.
Yeah.
The behavior, very much, I mean, clearly all of this points to, there's a lot of behavioral components to this, and including that, I didn't mention research, directions because I was trying to rush through, but, in any of these models, the behavior is important, just even in the dispersion models. And so it's something that should be included at some level.
It's kind of interesting that airplanes are known to be very dry. So that's what I'm told is another risk factor of being in an airplane.
I think, given the high air exchange rates and what we know about the decay rate of a virus in air is actually it's pretty slow. It decays pretty slowly already, even at normal humidity. And the air exchange rates are so high that I don't think the decay rate is going to matter, but what may matter more is the change in humidity on the, what are they called? The lining of your respiratory system, and how sort of more vulnerable you may be to infection.
Oh.
But if the air is dry and your mucus is dried up, the virons can't get into your nose because they need mucus to settle into.
Yeah, but it's never really that dry. And also remember that a lot of this, this virus is likely to be infecting alveoli and deep respiratory, right?
Correct.
So we don't know. I mean, maybe it doesn't matter. I mean, yeah.
Yeah, one thing masks do for you is increase the size of the initial puff, which is important from a dispersion point of view. You want to keep the initial puff as large as possible to have turbulence sort of tear it apart, because turbulence essentially stretches the puff in all directions. So the mask, of course, That's what I keep on telling my wife. Right now, arguments with my wife, I keep on saying, don't go to the grocery store, don't do this, because I'm writing a paper on this. So I said, well, keep the paper to yourself. I'm going to go to the grocery store with masks on. At least she listens to me there.
Glenn, we have one more question for you from Uma. Regarding the small number of sources being responsible for the majority of infections, the 2080 that you mentioned earlier, and the stochastic nature of the spread, could you comment on the need for backward tracing to uncover clusters suggested by Zeynep Tokefsi at UNC?
I still think you still need that, because this isn't a so everything about what I described was assuming aerosol spread by in enclosed spaces, but there's still the potential for other kinds of spread. Especially think about it. I think a lot of what happened at UNC during the outbreaks had to do was aerosol spread, but a lot of close contact. Maybe it was even outside, and so you'd still need to do that to capture those other elements of the transmission pathways that this kind of model won't capture, right? And also there's going to be, we still need to do that because it allows us to get better at understanding multiple interaction spread that a model like this doesn't necessarily capture. We could try, but yeah, there's a lot of human elements necessary to include in these models, behavioral and otherwise, that these backwards tracing help with, and also forward tracing. Both backwards and forward tracing are important, and really getting. And I really, that was going to be one of my suggestions, is that we really need to get the epidemiologists talking to the engineers and the scientists that are doing the sort of aerosol modeling and dispersion modeling and whatever. And really find a way to speak the same language so we can pull all this together in a cohesive way.
I want to add one more thing to mitigating risk is personal ventilation systems. They've thought about personal ventilation systems in the past. There are several papers written on it. I think that's one way of reducing risk substantially, is to have some system that sucks out there immediately. It doesn't allow it to go anywhere. Because basically, if you transport virons, it's going to infect people. We don't know exactly how many of them are needed to create infection. But personal ventilation system, even an aircraft, I don't know whether they're doing that in aircraft, but we are doing some work for some authorities, transport authorities here at UC Riverside. And one of the ideas is to have personal ventilation systems where every seat essentially has got a system that sort of sucks out the air, and fresh air is brought in from outside, but it's fresh air. But the seat itself sort of sucks the air out.
Glenn, I have a question. So this is an air pollution modeling conference primarily. So I want to bring up an analogy and have a question. The question is for air pollution exposures. As we all know, we have the NAAQS threshold, and we have adverse health effects based upon threshold, though there are emerging studies that show adverse health effects even at lower than threshold concentration. That's a different topic for later. But the question for this panel is there a threshold in terms of quanta or virion, in terms of how many are needed to be detective, corona positive, right?
That's a great question.
Question that's being asked by the general public a lot, and I don't think I've come across an answer to that.
No, I don't think there is an answer right now. Yeah, I don't think we have an answer. But
Okay.
but that threshold is likely, if there is one, it's likely above 10. 10 viruses, something like that. One probably is not enough, but it's not clear. I mean, I wouldn't want to hang my hat on it. We should probably talk to, those folks that are actually studying this in animal studies,
Okay. Steve or Venki, do you have any comments on that?
No, I don't know anything about it, so I'd rather not comment on it.
Okay. One more question for all of you. That may be the last question, unless the attendees have anything else. Are there any studies that you all have seen that show virus linking to other particles? Other say fine particles, ultra-fine or fine particles. Other studies that show transmission where the virus clings onto these particles and then get transmitted in the air.
Could you repeat that question? Sorry,
The question was, do the virus cling to other air pollution particles and get transmitted?
Probably. I mean, a virus droplet is essentially just a little enclosed aerosol, right? A little particle in air, and so if it collides with something, it's going to stick to it. So yes, and the higher the concentration of particles in the air, if you're in a polluted environment, the more likely it is to be associated with another particle.
Okay.
Yeah.
Probably there's a module in CMAC that will do that for you.
That's what I'm looking for, to see if there is room to add a module for that.
Oh, no, I think it's been studied a lot, as Glenn said, aerosol to aerosol capture.
Yeah. Okay.
The typical indoor environment, if there's nobody smoking, right? If you're in the US, the concentrations of let's say PM 2.5, something like that, is generally less than 10. It's really low, and so the collision rates are low, and so you don't have a huge amount of coagulation occurring. And so, but if you're in a smoky environment, you probably have more.
Sure. A couple of more questions from the audience. Indoor air is much drier during the winter. How much difference does that make?
It makes some difference. I mean, as you breathe out, the aerosols do change in size a little bit because they're drying out a little bit, and so the size of the aerosol does matter in terms of where it lands in your respiratory system. And so there are some associations there that could be part of the reason why we see more transmission during drier times. So yeah, does that answer the question?
Yeah.
I had a follow-up question to Glenn's comment here. So is the desiccated virus viable?
No, we don't know.
Okay.
And also, I mean, they don't necessarily desiccate entirely. And so the question is whether you have true drying down efflorescence, depending on the conditions, and maybe if the indoor dry, it can get dry, but it's maybe 20-30% relative humidity. And the question is, does that? You've also got a lot of proteins, salts, fats, and things that are present in these respiratory droplets. And so whether it actually goes to full dryness or not, kind of is, I'm not sure. I have to ask Lindsay Marsh, she'd know. She's done those studies. And in very dry environments, certainly. And what's also interesting is that those aerosols, if they go through the ventilation system in winter, they're going to go through a heater, and they're definitely going to dry. And they probably will not rehydrate. They won't. And so you're not going to, so now they're dried down. What are they viable? I don't know. Viruses aren't really all that, they don't last forever, right? And so they dry down. We don't know whether they're viable. Yeah,
They
probably
seem to
not.
be lasting forever.
Huh?
I said they seem to be lasting forever.
These seem to be pretty long-lasting viruses. That's right. That's right.
Glenn, probably the last question, if you can take this. So you showed the impact of universal masking with 90% compliance. Has there been any work to see what typical mask compliances is in environments where masks are required? My personal observation is that many fewer than 90% of people seem to wear masks correctly. That's people who have their nose outside of the mask, etc. What would reduction in cases be in more typical mask compliance conditions?
Yeah, that's a great question. I think there probably are. I don't have that. I've seen some, I would say, passive in reports, like people using numbers, and I don't know exactly where they're getting the numbers from. I think it really very much depends on where you are. It's culturally dependent to some degree, and somewhere between 60 and 80%. But I think this is also a very stochastic, very skewed phenomenon, and so that you will have many gatherings where the same, let's say, people of the same background, same culture come together, and they will be more likely to wear masks or not wear masks, if you know what I mean. And so there's a tendency to have if you have larger events, to have fewer percentage masks at those events, and therefore these are going to advance super spreader events.
Okay. Thank you. Oh, I thought we were done, but there's one more from Uma. This is probably for all of you. I thought it was suggested months ago that wetter aerosol would cause the virions to deposit out quicker. Also suggested as the reason that masks are effective at the source, that is the breath. Yeah,
so there is a relationship between the humidity and the size of the aerosols, but for the most part, if you're in wetter weather, the viruses they don't grow that much. I mean, they don't get that much bigger, and so the vast majority of these particles are of a size that don't settle out very quickly anyway. And so if you increase their size a little bit, maybe a few of them will settle out more quickly, but not many. And so I think this is a more of a hope than it was a reality.
Just a follow-up question with what Glenn was saying. I'm learning a lot, by the way, is what explains the extremely low death in Taiwan, death rate in Taiwan? I mean, basically, I think 23 million people population, and they have had about 10 deaths or something like that. I mean, is it universal masking that's helping? Because it's a fairly crowded island, very, very crowded. And yet the death rate is so small, minuscule by the rest of the world standards.
Well, I don't know. I mean, I'm sure that there is an answer to that specific question, but the masking in Southeast Asia has been quite effective. And it was during the first SARS outbreak. And and for the countries that take it on early on, I think what's happening is that very early on, before it spread very far, it's just they're dropping this reproduction number below 1 and are able to really control it before it gets out of control. So I don't know the answer, but I think masking is the answer.
Yeah, but I think your first point is good in the sense that Taiwan immediately, as soon as they heard about the infections in Wuhan, immediately started screening people from China, flying in. And Vietnam did exactly the same thing.
Yeah.
And the first case in Vietnam was actually an American tourist who was infected. But they also possibly have almost no deaths, Vietnam, because they essentially closed the border.
Yeah.
Okay, with that, I would like to wrap this panel up. Thank you to each of you for an amazing session and for all the information sharing and exchange of ideas. I also want to thank the audience for staying past 2:30. Sorry, we went a little bit late, but I thought it was a very important topic and very good discussions happening. Thanks to all the speakers for this important topic and covering the different issues associated with the airborne transmission that affects all our lives on a daily basis. With this, we also conclude the CMAS conference as a whole. I do want to thank all the session chairs, the plenary speakers, the presenters, and the conference attendees for a wonderful conference and for adapting to this new format, this virtual format. Also want to thank the CMAS Center team at IE, Dr. Back and Mr. Brian Ness, and the ESE students for planning and executing this event in a fantastic manner. We hope that we'll revert to an in-person event next fall and hope to see you all in Chapel Hill next October. Safe travels back to your living room or other.
Thanks a lot, Sarav. I really appreciate what you have done. Obviously organized a fantastic conference, and thanks for organizing this session.
Thank you all.
Thank you.
Bye.
Thank you.
Bye.
Bye.